exploit pack development. So this training is mostly focused on hooking and type of modern hooking techniques that are used by antivirus software and also EDRs. And so what I'm going to show you how it's done, how typically a hooking is done. And also besides that, we will also cover the unhooking available techniques in 2023 and some clever ways to basically bypass those hookings. I'm also going to show you why those hookings are in place. Besides that, we will also see those hooking in action. And also we will go to control pack, and we will see the unhooking in actions through one of our agents. So, but first we need to cover some basic stuff. So basically, when you run an application, how does the ABs? I'm gonna make it quite simple and quite basic, so it's easier to understand. But if you have any questions, feel free to drop the questions in the chat. I will, or you can also unmute yourself and ask directly. But basically, an antivirus or an EDR, what they do, they need to monitor the actions of a program of the software running during runtime, during execution, so basically during execution, and also once it touches something into the computer, meaning it's part of the disk, you can scan the disk or the hard drive or the memory if it's living on the memory. But at some point, it will try to find that piece of software that is trying to detect. So during runtime, I guess you know already how it is detected from the disk itself. So basically what it's going to do is going to look for the files and then check for signatures in most of the cases, pieces of the decompilation of the software, or sometimes just place of parts of the binary, and then it will check for that and trying to see if there is a match, or maybe there is more than one match. And then I will flag that particular software from hashes or pieces of the compilation itself. If it depends of, of course, it depends on the implementation of the antivirus or the EDR. How does it work out with this type of detection? But today we're gonna cover most of the runtime type of detections, meaning hooking in this case. So when you run a piece of software, then of course you need to interact with the rest of the operating system. So when you run something, you need to use functions that are provided by the operating system. Those functions at the end of the day, they being called as a Syscalls, and in a higher level, they will be functions. And then from there, what you want to do is to detect those functions, and those functions, they are part of, in most of the cases, libraries that are implemented by the operating system of your own program. So when you run something, let's say I have the antivirus here running, and what I'm gonna do, I'm gonna run a CMD. And of course, you can go deeper in what I just explained it. There is plenty of information on the internet for that. But let's say I'm running this CMD, and here we'll see that I have a new spawned CMD. So when I close it, it will get destroyed, see it in red. So when I open it again, just like that, it's green. Now I have the CMD here. So when I spawn this CMD, we'll get assigned a PID. The working set, the private bytes. This is basically the memory that is using the amount, and then of course you can see the CPU. But besides that, with this is from Sysinternals. This is one of the tools of Sysinternals. This tool is called Process Explorer. And here's something that you can do. Here you can click on Show Lowell PAN, and then you can see the LLs that are loaded into this CMD, right? So when I load this CMD, then you will see that a lot of DLLs are loaded into the same memory space of the CMD, of part of this the same privileges on the same memory space that is running. All right, and then there are more, because if I check on handles, you see that as part of these handles that are also part of the CMD, you see that I have the thread handle, I have two semaphores here, and then there are some keys that are registered and are being used and called by this CMD. And besides that, we have the files objects, and I also have two directories that are being called. One of them that is quite important is known DLLs, and these known DLLs is basically a symlink that will link a lot of DLLs that also are also loaded into in this case DCMD, but in most of the other binaries that you have running on your on your Windows. In this case, you will have also these known DLLs running. What are those known DLLs? So if I go to DLLs, you will see it here that I have a bunch of DLLs, but these DLLs, they are loaded from this to memory. But when you have the known DLLs handle loaded into your binary, that's most of the cases, you will have a bunch of DLLs that are also loaded into the same memory space. And why is that? Because there are a lot of DLLs and functions that are repeated, that they are used by most of the programs. So because there are other reasons, but one of the most important reasons is performance. So when you load functions and DLLs from, as I say, from disk, and you have to map those into memory, that that makes use of resources from your computer. So in order to avoid that, in order to avoid calling again and again and again the same functions and loading those into memory, you use a handle. So as soon as you boot your machine, then you will have those loaded into memory, and then they are just a reference to those. So if you open from sysinternals the Windows WinObject application from sysinternals again, so you can see, and depends of the version, you will see the DLLs, yeah, that are mapped. In this case, you have symbolic leaks and also sections from known DLLs. And again, if I go to here, handles, you'll see that is loading here. And all these DLLs, they are being loaded as part of the known DLLs handle. You will not see them when you click on DLLs, because they are linked by the handle, not by the DLLs referenced here by your binary. So why I'm explaining this? Because you might see these DLLs, and these DLLs, they contains a lot of functions that are as part of utilities that are used by every other program in your computer. For instance, WS232, this is used for sockets, and kernel 32 is used almost for every sim. Then you have like shell 32. You also have the one for crypto. There is a lot of DLLs that basically with these DLLs you can do almost anything on Windows in terms of functions, right? So that's why almost every other program is loading those. And just imagine if you have to load these DLLs every time, it will be catastrophic in terms of resources. So now that you understand how the DLLs are loaded and why you have no DLLs that are loaded here, and just imagine that you want to touch something from your program to disk, and you are an antivirus, and you want to know if what is that action is happening. So first, is that action happening from that program? Let's say this CMD wants to now it's a malware. This CMD, let's choose imagine. This CMD.exe is a malware and wants to go into the disk and remove some files from the Windows folder. That shouldn't be allowed, right? It should be flagged, and then it should trigger a kind of alert or try to block. It should be blocked by the antivirus, for instance, or at least flag it by an EDR. So if you are just forget about the EIT, here is important. He's just showing. I'm just trying to show you how our rootkit, not how our rootkit worked or how the import address table hooking work, but I just want to show you how a hooking work. Let's say replace rootkit by antivirus, because that's actually how it works. So replace rootkit for antivirus or EDR, and then this is your application code that is coming from, and I'm using here Win64, the x64 debugger. So I will also show you the same on IDA. So memory mapping on this one, I basically choose any other. So basically what you have on text, on the text section, this is what I'm showing here. Let's say it's part of the application code. And then, well, here it says import address table, but it doesn't matter. It's choose the hook of it. Because the hook it can be here, but most of the cases it is coming from here, but it could come from any other function, right? So when the application calls kernel32, that, as I show you, is part of the known DLLs. If I go to the Windows object, so kernel32.dll. So actually, if you debug this one, so if I come here and then debug. Oh, we can do it actually, but I don't know if we're gonna go quite deep, but maybe that's an exercise for you. So if you load a CMD into a debugger, EDA or Jira with the debugger extension or the debugger of your choice, and then you just put a breakpoint on the entry point, and then when you load the non-DLLs into the memory space of CMD or choose a simple program, and you will load kernel32.dll. So, and then you can stop that execution, go into the kernel32.dll and look at the functions. There is also kernel32 MSDN. You can also look there. Well, here's functions. If you don't feel like debugging, so here's a list of functions, and I'm just scrolling through those, and surely it will get your eye into some like create file, create directory, copy file. So you can imagine that all these functions, they are used by every other program. So when you do that, let's go back to I hate Zoom that it gets the menu here. All right, let's Oh, can you hear me? Yes, you can hear me now. All right, let's continue, guys. So I think there was something else, something wrong with the audio. I don't know until when did you hear me? Should I go on? I was explaining how these DLLs, they were loaded into the same memory space of the CMD of the process. In this case, is user is using a user access level. But if you run this as an admin, then they will also have the same privileges as that user. So yeah, please use the chat if you have questions or something. Let me see if I can bring the chat. Sorry for that. So yeah, I hate Zoom. I think I drag the Zoom top bar and then I mute myself by mistake. Let me see. All right. All right, I will choose continue. All right, so then we have this here. Then we have it running, and then basically an antivirus or typically an EDR or an EDR, what it's gonna do, because it's running with the DLLs running added to that binary, then the in this case the antivirus will also load their own DLLs there. So if I run this here, you can check that. If you, I don't know, just trying to install an antivirus on your machine on a VMware or a virtual machine, and then run CMD, and you also see that's a test that you can do. So run it on your machine on a virtual machine, an antivirus running, and then click on show lower pane, and then show the DLLs, the libraries, and then you will see here the DLL from your antivirus, the one that you pick for testing. So, and here I'm using the this one from Windows. Let me just turn it off. So why is it doing that? Because it will try to hook. So basically the hooks that I show you will hook all of those from user level, from user mode. And then from user mode, it will try to monitor all the functions and and act upon if it detects that something is wrong or something is needs to be flagged. All right. So there are multiple ways, multiple techniques that you can use, and here I have a list of some of them. One is a section remapping, that is basically reloading the hooked TXT sections in memory. So as I said, when you load a binary and your antivirus program will inject itself. So it will inject itself into the same memory space of your program, and it's gonna hook all the DLL, all the functions, not every function, but all the functions that the antivirus think that might be dangerous. So it depends on antivirus and antivirus, and you can Google some of the, so you can Google antivirus name plus hooked functions on Google, and then you might get sort of a list of those, or you can reverse engineer the DLLs that are injected into your binary if you want to get a full list of exactly the hooked functions that are actually hooked on your program. So when you do that, then you will then you will see exactly the hooked functions. But here, what with section remapping, it means that we will go into the text section of your program, and then it will reload from text, so the unhooked version of the hooked functions, and it will just basically make a clean one with a clean state of a program. So let's say you have here the hooked function. So because it's going here, then what it's gonna do? So let's say we have a hook in create file, then it will load an unhooked version of a create file that doesn't have the hook, or reload the import address table without the hooks, right? That would be a remapping. Prologue Restoring will be overriding the first byte of the hook with the known original byte stored in the unhooked program. So then it will replace those bytes. The Perun's fart override the hooked txt version with a code of not yet hooked, in this case TDLL, in a created suspended process. So basically, because the hooks they are injected in real time, what you can do is to run a program in a suspended state. So make a breakpoint on the entry point, and then check for the NTDLL in this case, and then check for all the hooks that are not that are on your program, and then replace those with the unhooked ones from here. So that way this is like I think it's like a joke name, but instead it should be pre-run execution or something like that. But override, basically what it does is replace the text section with what has not been unhooked. It's quite similar to this one, but it's quite different because it's doing it from memory, because it's taking it from the unhooked version during runtime before the hooks were in place, and in this one is replacing the unhooked versions of your functions from disk themselves, right? So let's say if I check for create file, and this one is, I can check create file against the original one, and instead of running it, I will say, hey, don't run it, because I know it's not the original one. Then I will choose replace this one with an unhooked one from disk. And as you can imagine, all what I'm saying, you can start thinking about it. The original time tracing, found the original code in memory, analyzing the code of the hook, and alter the hooks there. That's basically directly in runtime doing that. And then interprocess function copy, override hooked function bytes where the original bytes found in another not hooked process, because as I say, they are processes that are not hooked. They are not being hooked, so you can check for that doing runtime in memory, and you can also interprocess section copying. So basically, these two are quite similar. There is overwriting the text section in memory with the original text found in other not hooked process. They are both quite similar. But as you can see, all this, what I'm saying, from all of this, what I'm describing, they all require some user interaction. So how do you do user interaction without being detected? So because that's happening during runtime from a user level. So how do you actually can do a bypass to implement these unhooking mechanisms? Then you can do something that is called Syscalls, direct system calls, because at the end of it, if you go deeper into this, you will see that create. So you call this, then you call here. If you have the hook here, you have create file. But how do you call create file directly? Bypassing the import address table, because these memory offsets, they are random. They are not randomized, but they're quite saved or randomized. So the offsets, they are not similar. So you cannot choose come here, and if you cannot come here directly. So you have to come here using the EIT. the import address table. So you can use Syscall Whisper and then load some libraries into your program when you're compiling that program. So basically, if you want to implement any of this during runtime without being detected, the implementation of these techniques, it has to be done using, it could be anything else, but this is what it works best now, is to use Syscall direct system calls and directly call create file, avoiding as a whole the import address table and then doing the unhooks. So when you do the unhooks, you do it using direct system calls, right? Direct system calls is using an alternative to the IAT or an alternative to basically the way you call functions on Windows. You can go deep into Syscall Whispers. You can find the code on Git. Now let me show you one of the from what I show you, an implementation of it using exploit pack. But first, sorry, control pack. But first, let me show you. So I open a CMD, and then using that CMD, I'm gonna connect to it using IDA. There you go. And then let's look for this PID. That should be this one. 964. If you go to 964, okay. Now it's loaded and the execution is paused. And then here you can see the DLLs that I have on this one. And if I go into kernel 32, it's just to show you that I have this, and of course I have all the sections. Oops, sorry, wrong one. Here. I have all the sections loaded here. And if I go into kernel 32, I can go deep into each of this one, or I can choose, let's say, create remote thread, and I can, if I open it, I can see here where is it, and then I can, of course, put a breakpoint or something. If I ever hit this, I will hit this breakpoint. Actually, that's a good try, because if I go for create a file and then put a breakpoint here, and you see that create file is not here, but it's a jump to here. It's a jump to this reference. And you can follow the offset, and it's going actually there. And if I put a breakpoint on here, then if I create a new file using that CMD, if I create a new file using this CMD, then I will choose hit that breakpoint. So that's something that you can try to see and check. But let me show you on, so before we run out of time, let me show you an implementation of it with control pack. So I have control pack running, and what I'm gonna do, so if we go to control pack and then DLL shell, and here if you pick the DLL library implant, and then you select unhook known DLLs. What it's gonna do is gonna look, so the binary that you are gonna be running, that actually you also have the source code on the folder of a control pack. Then you can modify, this is the source code if you want to compile it yourself, or read how this is implemented pragmatically in code. What it's gonna do is gonna look for all the DLLs that are listed in your system under known DLLs. So whatever is listed here and is loaded during runtime, and if there is a hook there, because it's gonna cross-match whatever is loaded with whatever is on this, and then it's gonna do a section remapping. This is gonna do a section remapping and reload everything from the text section from the original from this during runtime, and it's gonna be doing all of that using direct system calls. So let's do that now.
New remote agent connected.
So there's a new remote agent connected, and you can see, so it detected that I have on this virtual machine, when this has been running, it has detected that all these were mapped, were found, and then it unhooked all these DLLs. So after checking that these were there, then it unhooked all of those. And after that, right after that, injected, after doing that, it checked the DLL agent. So now if I go to control pack, then I have a new DLL here running. If I click, I can see how I interact with it. And then if I click on, for instance, a screenshot, I can ask for a screenshot, and I will, yeah, can see how this works. There you go. So guys, so you can try yourself this. Of course, you can interact with the agent, and everything that is happening here right now after the unhooking of those, it cannot be detected by the antivirus because everything has been unhooked if you have an antivirus running. At least if the functionalities of the antivirus, that is 99% of the cases, relies in user mode to hook and detect by hooking those malicious actions. That doesn't mean everything what I'm saying, direct system calls, the type of hooking. So it doesn't mean that this will works always. It's working now, 2023. Surely it will work for the next few months, but it might happen that a new technology or a new way of doing things will appear. So and of course it's always the game of the cat and the mouse, and of course we will keep on updating the mechanisms for detection that we have. All right, guys, I will stop sharing now. I hope you enjoyed the training. Sorry for the mishap with the audio, and yeah, and hope you enjoy it, and hope you I will see you again the next time in the next training. Bye for now. Thanks, guys.